So let's talk about how do we check if a vector field is conservative or not. And this is the one that we'll be checking. First, if a vector field is conservative, that means we can find a function f of x, y, z so that the gradient of it is equal to the vector field. And the idea is that if you take the partial derivative with respect to x of the function, you should get this. If you do it with respect to y, you should get this. If you do it with respect to z, you should get that. But of course, it's hard to just think about a function out of nowhere and then satisfy that. So we should have a way to check it. And there's a very nice theorem that we can use. What we are going to check is the following. If the curl of our vector field is equal to 0, and since the result of a curl is a vector, so this is technically the 0 vector. If we get 0, then we are on the right track. And there's a small detail. And these components here, usually you can call them P, Q, R. So just say P, Q, R have continuous partial derivatives. If this and that are satisfied, then we can be sure that our vector field is conservative. So if you check this part first, then you can see that differentiate all of them, they're just like polynomials, so of course it's always going to work. So this right here checks. Now we just have to compute the curl. So by definition, curl is the del cross the vector field. And this right here is just going to be the determinant of a 3x3 matrix. Set it out like this. We have the I, J, K components right here, the unit vectors for the first row. And then right here we have the operators, partial with respect to x, partial with respect to y, and partial with respect to z. Now for the third row, you just enter PQR right here. So 2xy minus 4, and then x squared plus 2y z cubed, and finally 3y squared z squared. This is a square. Okay, first we do the cofactor expansion starting right here. So you delete this, delete that, you do this times that, but what's happening is you are doing the operation, the partial derivative with respect to y of this thing. So take the derivative of this with respect to y, you get 6y and then z squared. And then minus, do the partial right here with respect to z. This will give you 0. Bring the 3 to the front, minus 1. That will be 6y z squared as well. And that will be with the I right here. And this is 0. That's good because we are on the right track, right? And then continue. Next, when we do the cofactor expansion right here, it's a minus. So keep that in mind. Be careful with that. Delete this, delete that. Do this and that. Partial with respect to x. There's no x, so we get 0. Minus. There's no z, so we also get 0. Super nice. Lastly, for the k, it's plus. And get rid of this and that. You do this times that. And you are doing the partial. We get 2x. There will be 0. And then do this. That will just give us 2x because the derivative y is 1. So just that. And then k. Well, 0, 0, 0. So indeed, we end up with the 0 factor. So this right here checks. And as I said earlier, this also works. So that means there is a function, little f, that will satisfy this. Now let's see how we are going to find it. So here's the idea. Now we know this f exists, and we know the del of f is equal to the vector field. So that means if we look at this function and take the partial derivative with respect to x, we will get the first component here. So let me label that with f sub x. Similarly, for this right here is the partial of f with respect to y, and the last one, f partial derivative with respect to z. And you can start with whichever component that you want. I'm just going to start with the first one. So f sub x is equal to 2xy minus 4. Well, I want to get back to the original function f. We took the derivative with respect to x already. We just have to integrate it with respect to x. So we can get the f right here. And integrating this in the x world, just focus on this part, we will get x squared, and y is a constant, keep it. Integrating minus 4, we get minus 4x. But we have to add a constant. But in the x world, y and z are both considered constants. So we add a function, let's say g, in terms of y and z. So that's how the function looks like. Now, we just have to figure out what g is. We will have to use this and that to help us out. This means we look at the function f and do the partial with respect to y, and we end up with this. So I will look at this equation and do the partial with respect to y. Then we get f sub y equals the derivative of this with respect to y. Here we have 1, so it's just x squared. And then minus 4x. There's no y, so just 0. This right here, I will just say plus g sub y for the partial of g with respect to y. This right here shall match with that, so I'm going to set this equal to x squared plus 2y z cubed. Now, x squared match. That means g sub y shall be equal to this. So that's my next condition. I need to figure out what g is. Let's go ahead, integrate it with respect to y. So we get g, that's equal to, just look at this part, we get y squared, and then z cubed is a constant. And in the y world, z is a constant. So right here, I'm just going to add another function. Let's call it h, and then that will be in terms of z. So this is how g looks like. I'm going to put it back here so we know f looks like x squared y minus 4x plus g, which is this, y squared z cubed plus h of z. Now, to use this, that's f sub z. So I will look at this equation, take the partial with respect to z. So we get, this will give us 0 because there's no z. Likewise, that will be 0. And for this, bring the 3 to the front, minus 1, 3y squared, z squared. And this right here is just the regular derivative. I'll put on h prime of z. Okay, this thing should match with that. So I'm going to set this equal to 3x squared, z squared. So this and that match. But how about this? That means this right here should be equal to 0, right? Because this is like plus 0 here, and plus 0. So that means h prime of z is equal to 0, and then integrate both sides, but the only way to get the derivative of some single variable function is equal to 0 is that function is just equal to a constant. But right here, I'm not going to put on c, because when we're doing these kind of things, when we're dealing with line integrals, we'll be talking about curves, and that will be the c. So for this, we'll use k for the regular constant. And that's pretty much it. I just have to put this back here, then we can see our function is equal to x squared y minus 4x plus y squared z cubed plus k. That's it.